Alright, now we've started onto electromagnetism. I wanted to start just by giving you a little bit of a reminder of where we were at in level 1. If you had a wire with current, the arrow, as you should be aware, always indicates that current is going from positive to negative. It's sort of like they pretended that the current was positive charges because they came up with a system before they discovered the electron. Now, we learned about the magnetic field that would go around a wire. And this was pretty weird when it was first discovered because it was a circular sort of field. No one really knew what they could do with it. But the right hand rule was the one that we used to predict it. Right thumb in direction of current, fingers then wrap around the wire indicating the direction of the field. So the field is sort of like just a circular direction around that wire. And so magnetic fields go in circles. They are circles, and so this is indicating our magnetic field, and we had a symbol for it which was B, and the units were Teslas. Let's just use the symbol T. We had an equation for working out the strength of the magnetic field around this wire. B equals mu naught times the strength of the current divided by 2 pi and then divided again by the distance to the wire. This, as you have been doing physics for a while, current is in amps and distance is in meters. One of the things that we did do in level 1 was that we often would combine that mu naught divided by 2 pi into one symbol called K, and that's because mu naught actually equals 4 pi times 10 to the minus 7, so when you divide that by 2 pi it just equals 2 times 10 to the minus 7, which we called K. So that was often done in exams like that. This mu naught is just a magnetic constant for space. Now, and what were the little tricks we learned in level 1 with this? D, often if they gave you the units in millimeters, you needed to convert to meters, which means divide by 1000. So often you just go, okay, I've got 2.3 millimeters, but 2.3 millimeters times 10 to the minus 3. 10 to the minus 3 is dividing by 1000. It will convert the 2.3 millimeters into meters. It's just like moving the decimal place 1, 2, 3 places, that negative 3. It's like 3 places to the left, whereas plus 3 would be 3 places to the right, right? So converting millimeters, if it had been centimeters, 2.3 centimeters, we've just gone 10 to the minus 2 and moved our decimal place 2 places that way. That's just a quick way to put it into your calculator, or you could just do it in your head that way. So we did calculations like that. We had to always work out directions. So we had examples where we might have a wire going down with a current in it, and we might have another wire here, and we'd have to work out, okay, right hand rule, this wire on the left, current goes in from the wire on the left, and from the wire on the right, current comes out, and then we'd have to subtract them. So that was the sort of thing we did with magnetic fields around a single wire. What we also learned in level 1 was that the magnetic field, if we put it into a coil, then ran a current through it, because you have to run a current through a wire to get the magnetic field, then we would get a very similar magnetic field to a bar magnet. And we'd already learned with our bar magnet that the magnetic field lines come out of the north and they go back to a south. Shouldn't be crappy like this, but I'm just doing a quick review here. So magnetic field lines go from north to south, and inside the magnet they go from south to north. Magnetic field lines are always closed loops. So they do continue on through the magnet and out the other side. So the current, if you put it in this solenoid and wrap the loops, all the magnetic fields from those bits that go around the wire go in the same direction inside the hole inside the solenoid. And so you've got like this tunnel with the magnetic field going through it, and it produces the same effect as a bar magnet, and we call that the solenoid, but basically it's made what's called an electromagnet. And we found that by increasing the strength of the current, we could make the magnet stronger, or by increasing the number of turns per meter, or by putting an iron core in there, because in the iron core all the domains, which are the little magnetic areas in a magnet, line up, strengthening the magnetic field. So we learned a few things about solenoids and how they resembled bar magnets, and we could do it with electricity. This was wonderful. We learned the solenoid rule, where we would wrap our fingers in the direction of the current round a solenoid, and then our thumb would point towards the north. That was the right hand solenoid rule. Now, magnetism on Earth was a little bit confusing. Well, it wasn't, but when we had our Earth, you may have got a bit confused, because if that's our south geographic pole and that's our north geographic pole, we know we've got magnetic field lines, but we had already learned that magnetic field lines go from north to south. So what that means is that there must actually be a physics north pole at the south pole, the south geographic pole. So there's actually a physics north pole at the south pole. And so that means at the north pole there must be a physics south pole. And the field lines actually, bring that back a bit, into the, and do the closed loop things. So you've got field lines running right through the Earth. And as usual we go from north to south physics wise. So there's actually, let's get rid of that north pole. And we've got a south pole up there, and they enter there, go there. And so inside the Earth, just like inside a magnet, they go from south to north. Now if you put a bar magnet near a field line, it points in the direction of the field line. Up here at the south pole, it will point towards the south pole, and at the north pole it will point away, because that's the direction the field lines are going in. We learned that where the field line spaces are big, that's where the field is weak. Bigger spaces means bigger or weaker field. We learned that the magnetic field itself was a place where a charge, a moving charge, would experience a force, a magnetic force. So the field is where a magnetic force is experienced. We could answer questions like, so if this little bar magnet points towards a magnetic south pole, then the top of the bar magnet, the little tip, the little arrow, must be a little north pole, because we know that opposite poles attract and same poles repel. You've felt this. So that's the basic stuff that we learned in level 1. So that's just a brief review.